Okay. Hello everyone. This is going to be the beginning of my presentation for OFDM1, Orthogonal Frequency Division Multiple Access. I'm Thomas Honeywell, and this is for the final project of VEL 6509 at the University of Florida. First off, I'm going to talk about the wireless channel characteristics and everything that impedes it. Seriously does impede it in modern wireless communication systems. These ultimately include multi-path fading. This is due to signals reaching the destination from multiple paths. Once they're transmitted through the channel, they all gain different channel gain and time delays, and all arrive at the receiver at different times. Another one is delay spread. Due to this multi-path propagation, the symbol durations can get extended, and they can interfere with the next incoming symbol. For frequency selective fading, the transmitted signals can exhibit significant signal attenuation that can alter them that have a bandwidth higher than the coherence bandwidth of the channel. Due to this, complex channel equalization techniques can be employed to reduce this. Can be explained further. And also interchannel interference. Bandwidths of different transmitted signal frequencies tend to overlap with each other in the frequency domain, which can cause error and cause inter-symbol interference of the receiver. First off, the main concept of this orthogonal frequency division multiple access is, of course, frequency division multiple access. It is based off that, where different subcarriers are made, allotted to different users, or different frequencies for them to be transmitted over their own certain frequency. They're all split up into several subcarriers, and there's a separate guard band in between them to prevent from inter-symbol interference. The OFDM1 ultimately builds off this concept and adds in a certain twist to it. You'll see in a second. I'll explain it further. You can see the OFDM1 concept, orthogonal frequency division multiple access. It's similar to frequency division multiple access. The twist that it gives to it is it adds orthogonality. Basically, it takes all those subcarriers and puts them real close together and transmits them and models them in a way that each symbol is transmitted in a way to not interfere with one another. If you look closely at all the carriers, at the peak of each carrier, you'll see when all the other adjacent carriers looks like they're interfering with it, they're at the null value at each peak. So if you set up the receiver to sample at each peak, the adjacent carrier frequencies will be at their null value and thus avoid inter-symbol interference. And also, as you saw in frequency division multiple access, there is a special kind of a guard band. Orthogonal frequency division multiple access also uses this. It's called the cyclic prefix. And for one, once the symbol is done transmitting, there's a feedback mechanism done where it transmits the end of the OFDM symbol to the beginning. So for the receiver to correlate that, this also, for one, needs to be at least as long as the total delay spread of the channel, of the multipath channel. And also, two, the reason it can do this and it helps avoid inter-symbol interference is because of this feedback mechanism, the linear convolution can tend to turn into a circular convolution at the receiver during the fast Fourier transform sampling, and which greatly simplifies the receiver design. And it can be all the multipath propagation within the channel will turn to be scalar components, and the whole channel can just be modeled as a simple circular convolution during the fast Fourier transform phase in the receiver. One downside of orthogonal frequency division multiple access is the issue of the peak to average power rate. This is due to the phases of all the many subcarriers tend to align at the same time, which will cause certain peaks in power. This, of course, can significantly increase the power consumption of the transmitter due to the need of a power amplifier or the high DC power consumption at the transmitter, which is ultimately a downside to many mobile communication systems. That is a hot topic, is the reduced power consumption. And certain amplifier methods can be used to mitigate this. One in particular is an idea of clip and filtering. That's one common way of dealing with this. However, it can tend to distort the OFDM signal as well, and therefore increase the bit error rate. So if you find a certain thing in your design, if you alter the clipping and filtering methods within the OFDM design, you can achieve both a low peak to average power ratio and a low bit error rate. This is the generic diagram of the OFDM transmitter. As you can see, it passes through a typical QAM modulator, and it tends to be, it could either be 16 QAM, QPSK, 64 QAM. Those are the common modulation methods used. Once they're doing this, they're passed through a serial to parallel converter, and each symbol contains 2 bits, one amplitude and phase, and then useful information is transmitted over these symbols by adjusting the amplitude and phase so those derived for the corresponding data stream. And as they're passed through the serial to parallel converter, due to the fact that there are parallel and sometimes can go up to 1,200 symbols in parallel, at first glance it can seem like it could be a complex hardware issue due to needing 1,200 oscillators in order to transmit this. However, due to advances in digital signal processing technologies, certain inverse fast Fourier transform hardware just simply converts the parallel frequency domain signals into several samples of one composite time domain signal, which is much easier to replicate at the transmitter. And once it does that, it also adds the cyclic prefix, as you can see there, at the end of that time composite frequency domain composite time domain signal at the end of that, before it's passed to the digital analog converter and ultimately onto the carrier wave to be transmitted. And once it does that, it just simply gets transmitted over air to be received at the receiver, and it's ultimately all reversed to achieve your desired information. Also, I'm going to talk about another thing in my project is the concept of code division multiple access, which is the predecessor of orthogonal frequency division multiple access. And this one, it's several transmitters transmitting simultaneously at the same time, utilizing the term of the spread spectrum technology. And the whole idea behind the spread spectrum technology is it spreads the entire signal power over one large bandwidth. And each transmitter and receiver correlates with one another with a certain pseudo-random code, orthogonal code, that only the transmitter and receiver know. So they're designed to be orthogonal to each other. Their data is XORed by a certain spreading sequence that's known by each transmitter and receiver. And as long as every user is operating more or less at the same power level, any interfering signal with the receiver will just appear as noise. It will just appear as a Gaussian